the paper that I'm presenting is a comparison between audio and IMU data to detect chewing events based on an Earable device. The author of this paper is Roya Lotfi, which I will be presenting the paper. Professor George Zanatakis, Professors Rashid Eskicioglu, and Professor Kurangirani. So this is the outline of what I will be speaking about. First, I will talk about the motivation of this work and tell a little bit about previous works that have been done in this area. And then we talk about what's the problem, and we point out our contribution of this paper. Then we talk about dataset characteristics and data collection method and the methodology for detecting chewing. And then I will talk about the results of this study, and I go through the discussion, limitation, and future works, and the conclusion. So the motivation of this work was that nowadays it's feasible and it's easy to collect various data from built-in sensors or wearable devices. And so we try to help individuals with their eating behaviors. And the motivation of this work was that according to statistics of Canada, 1 out of 4 Canadians are classified as obese. And the prevalence of obesity has tripled during the past decades in the whole world. And so also the studies on mindful eating suggest that a higher BMI is associated with lower mindful eating. So there was a study done by one research previously that mentioned that consumed meal proportion was increased by 71% as a result of watching television while eating. So there have been many previous work in the area of detecting chewing based on head-worn wearable devices. Some of the works have been done by putting an IMU sensor in the temple of glasses and measuring the vibration and detecting head movements while eating. And there was some works that was done by detecting movements of muscles, temporalis muscles, when they stuck one IMU data or accelerometer data on the face. And some works just used a normal earphone to get the audio data and detect chewing. And some other works used behind-ear IMU to detect the movements of the head. And also back IMU have been used and microphone placed inside the collar. So the problem that we were trying to solve was to investigate whether chewing can be detected by audio and IMU data of a eSense device. So this was a normal earphone device that had 6-axis IMU data and a microphone, and a Bluetooth and BLE where the IMU data was transferred by BLE to the phone, and microphone and audio data was transferred by microphone via Bluetooth to the phone. So inspired by many works on detecting chewing, we decided to use this device as it has a microphone like previous works, and also the accelerometer data. We were assuming that accelerometer data can detect the oscillatory movement of the temporalis muscle while the participants are chewing. So the contribution of this paper is assessing if chewing movements of the head can be distinguished from other head-related movements while recording IMU data, assessing if chewing sounds can be distinguished from speaking, watching television, and as well as silence, and comparing IMU and audio data and see if IMU provides better accuracy or not, and demonstrating when fusing both modalities how our algorithm will improve. Can it be easier to detect the chewing? So we decided to start collecting data from participants. So we had this idea that we want to just focus on sedentary activities. So we made this list of non-eating activities, which are sedentary activities, including speaking, reading, watching a short movie, drinking, and sitting still, and as well as eating. So we try to collect these data from participants and see whether chewing can be distinguished from other activities. And we developed an Android application to collect accelerometer and gyroscope and audio signals from the eSense device that we have been using. We set the sampling rate to 48 kilohertz for audio data and 60 hertz for IMU. And we recorded participants' video throughout the study to label the ground truth of each activities. and to synchronize the sensor data, audio and IMU, and also with the video, we asked the participants to nod 3 times and say start recording is started. So we conducted a pilot study at a local university within the lab environment with 5 subjects. 4 were male and 1 was female, age around 25 to 29. And participants were required to have the foods that are mentioned here. And we used different types of food with different texture, and we had this assumption that they provide different sounds and also different vibrations to the face. So the participants were supposed to eat chips, which is very crispy and hard, and pretzel, which is less crispy and hard, until banana, and banana was considered as a soft food. And each participant was supposed to have each of these foods for 150 seconds. And here is the picture of the snacks that we used in this study. So overall, all the participants spent 13 minutes on eating and 30 minutes on non-eating activities. And this is a sample of the data that we have been collecting. I brought it to show what the difference between chewing and non-chewing activities. The first one is for chewing pretzel. As you can see, the amplitude of the audio is high, while when the user was eating banana, the amplitude was much lower. And this is for the speaking signal. And also this is the IMU data, accelerometer in x-axis. And as you can see, there were some vibrations in accelerometer data while participants were engaging in eating activity, while those vibrations does not exist while the participant was speaking. And clearly there is some difference. We try to use machine learning algorithm to detect both eating and non-eating activities. So the methodology was that we used a machine learning pipeline for chewing detection. The first pipeline had 2 steps of feature extraction and classification, and we solely used audio data. In second pipeline, we used IMU data, and finally we merged both pipelines to use both of the IMU and audio data. So for the audio data, we set, as I mentioned, we set the sampling rate to 48 kilohertz. We framed the signal into 3 seconds non-overlapping time window. And for each 3 seconds, we divided it into 45 partitions. And we calculated the spectral centroid. So for each 3-second time window, we extracted the 45-dimensional feature vector. And for the second feature, we used male frequency Kepstrel coefficients. We decided to use 45 Kepstrel coefficients for each 3 seconds. So overall, we had a 90-dimensional feature vector that we fed it to classifiers, logistic regression, decision tree, and random forest. And the evaluation matrices were tenfold cross-validation and leave one subject out. And in the next pipeline, we used just solely IMU data. We set the sampling rate to 60 hertz. So here we both use time domain and frequency domain features at the time, because different movements provide different amplitudes in the time domain. But we didn't use time domain features on audio data because loudness was not a good feature for us. So we used a mean variance, power, and power of each 6 axis of the IMU data. The frequency domain features were same spectral centroid and MFCC, and we did know that originally MFCC was not designed for analyzing IMU data, but we empirically tried it and it had a good result, so we kept it. And overall, the 96-dimensional feature vector was used to train the same classifiers and the same validation techniques. So another pipeline was merging both IMU and audio data using these 2 sensors. So we concatenated the 90-dimensional feature vector with the 96-dimensional feature vector, and then we got 186-dimensional feature vector, and we again fed it to 3 classifiers that we mentioned before: logistic regression, decision tree, and random forest. So as I mentioned, to compare the performance, we used tenfold and leave one subject out, and our matrices were accuracy, precision, recall, and F1 score. So this is the result that we obtained for audio data. And as you can see, random forest with 94% accuracy using tenfold was the best, and also 91% for leave one subject out. And for IMU data, again, random forest had the best accuracy and best performance by having 95% accuracy, and leave one subject out had 94% accuracy. And again, random forest outperformed all other methods. And by tenfold, and fusing both sensor data got 97 accuracy. And again, random forest had a better results compared to other two classifiers. And this is the overall result that we try to compare both the modality, sensor modality, and also the classifier. And as you can see, fusing both IMU and audio and using random forest had the best performance, both by using tenfold and the one subject out. But and then after fusing both, then IMU was better, and the last one was audio. So in the discussion of our work, overall in-ear IMU data performed better for chewing detection compared to audio data. Random forest was better in distinguishing eating from non-eating activities based on both modality and combining both of the modalities. And in addition to higher accuracy, IMU data was advantageous over audio data because it's non-intrusive. It doesn't capture audio, and it's more private. And IMU data consumes less power as a result of lower sampling rate and fewer processing requirements. And IMU data, however, IMU data is noisy and sensitive to the movements. For example, if the users were both running and eating, it couldn't detect. But also our focus of work was on sedentary activities. So if a user is engaging in more complicated activities, we need to use more signal processing method to extract different activities and detect the chewing. And so to realize why IMU worked better, because intuitively we thought that audio would work better. So we assumed that maybe it's because of the softwood, maybe the audio can't capture the softwood. So we removed banana, which was the softwood from this study, and run all of the experiments once more. And we realized that by removing it, the audio's performance increases so much. However, IMU, we don't see that much change in IMU data, and fusing both IMU and audio. So based on two evaluation matrices, removing softwoods could increase the accuracy of the audio data because it was quiet and the microphone couldn't capture it. So the limitations of our work that I can point out is that we use two features for frequency domain features, which are spectral centroid and null frequency capsular coefficient. We could have used another methods like other signal processing feature extraction techniques and see which one works better, but we use just one. And the second limitation is that we just detected data, we just collected data while the user were only engaging in sedentary activities. While in real life, if you see individuals engaging more complicated activities like watching TV and at the same time having their meal. So we just had a very controlled environment, and we tested our algorithm just on very controlled lab environment. And for future works, so to deal with the first limitation, we plan to implement more signal processing feature extraction techniques and evaluate which feature extraction technique works better than like using just an empirical method. And to address the second limitation, we should collect a more comprehensive data set that involves a wide range of human activities that are more close to real life than the lab environment. So in conclusion, what we did in this research was that we investigated the feasibility of using Earable as a platform for detecting chewing. We evaluated the performance of built-in IMU and microphone sensor of eSense device. Separately and simultaneously when using the same feature extraction and also same classifiers. And IMU outperformed audio data by having 94% accuracy, 87% precision, and 92% recall, and 89% F1 score. And we demonstrate that the reason behind better performance of IMU data is that IMU data is robust against soft foods. And while removing soft food, it changed the accuracy of the chewing detection or by using audio. And we came to this conclusion that combining both modalities have the highest accuracy. And we identified the limitation of our study and proposed future works to fill in the gaps. And the ultimate goal of this project is to assist individuals in mindful eating by detecting their eating activities in real time and providing useful feedbacks for them. So thank you for your attention. Any questions?